So that would be from the gate perspective of the gate terminal. But if we are thinking on the circuit level, then very often we want to understand what are capacitances related to different terminals. We're going to speak in this part about the second order effects in MOSFET transistors. I think that's a really interesting part. We have to go a little bit more into understanding of the effects that we will see even more, some of them like channel length modulation, we will see more stronger in the advanced processes. And it's also a good starting point to talk later about scaling of the technology. But one more missing bit for scaling of technology is also understanding how the transistors are built, some nuances behind the structure and fabrication. So in this part, the topics to cover are about the threshold voltage and the related body effect. In the linear and the saturation region, we will have the on resistance, and in saturation region, channel length modulation, then subthreshold operation, and something related to more, it will be more important for the transistor-based circuits, which is the MOS capacitance. And finally, a few very simple examples, like introductory examples to MOSFET-based circuits. So let's start with the MOSFET transistor threshold voltage. I've placed here those two questions. How big is the threshold voltage? Or more importantly, what does it depend on? Because the absolute value will change with the technology nodes, and the parameters of the transistors also change with the technology nodes. So these are the two important parts. So let's have a brief recap. What is the threshold voltage? We can see it at the transfer characteristics of drain current as a function of gate to source voltage. We can see that there is the accumulation, depletion, and strong inversion. And the border between depletion and strong inversion is where is the threshold voltage. And very often we will say that below the threshold voltage, the transistor is not conducting, and above it's on state. Well, we will see today that there is this important regime called subthreshold operation, and some circuits are actually solely basing on this subthreshold operation, especially if we want to achieve low power. And then we have the strong inversion, where the model that we have already seen for the current equation of the drain current of the transistor is valid in this strong inversion region. And another thing to remember from the previous part is the definition based on the band diagrams, the definition of the threshold voltage. This is the inversion under the channel that is strong enough that we can tell that the effective level of doping under the channel is the same as the level of doping, but of the opposite polarity of the, in case of PMOSFET transistor, for example, it will be N doping of the bulk further away from the channel. So thinking about that, can you already guess what the threshold voltage will be dependent on? So what I was just talking about is the difference in doping under the channel and dip in the bulk of the opposite type. So doping actually will have some importance. And also what we can expect that will have importance is the flat band voltage. So that this is related to the materials that the transistor is built of. And we had without the applying any voltage at zero bias, we already have some bending of the diagrams because of this flat band voltage. Let's look on the complete list, because there are some things that it's easier to see already in the equation and in the list to have the overview. So what you can see in the middle is the threshold voltage expression, which is the flat band voltage. Then we have the Fermi potential and also the intrinsic potential, their difference. So that's what we were comparing, the difference close to the surface and far in the bulk. So here we can see that this will be dependent on the doping level. And whereas the flat band voltage depends on the material. So one more point is that we have then the gamma parameter, and gamma is so-called body factor. It's shown in the corner. It's dependent on the dielectric properties, oxide capacitance, and also the doping level. And finally, in the end, also we have the dependency of source bulk voltage. And I think that the source bulk voltage dependence is really something that it's worth spending a few minutes talking about because it's not obviously intuitive. So what happens here we see in this expression is that if we increase the voltage difference between source and bulk, normally most often we think that source and bulk are connected together, and then we modify the gate voltage to switch the transistor more on or more off, and then we apply the drain voltage higher or closer to zero to create the voltage potential between source and drain so that to have current flow. But here is the fourth terminal that comes into play, which is the body. And we see that if the body bias, which has to be, we have to have the reverse bias diode between source and drain, source body and drain body. So if this reverse bias is more negative, then the threshold voltage is increasing. So let's have a look into this effect. And what I would like to show is that we consider two different structures. And what we might first think of is this simple MOS capacitor. And the second hand, on the right-hand side, we have MOSFET structure with source and drain as well. So on the capacitor structure, which is on the left, what we have is that there will be the depletion region, and the depletion region tells us where is the threshold voltage, where we can talk also about band bending and the threshold condition in this case. But this is only related to two terminals, the gate and the bulk. And so it's only dependent on the gate bulk voltage, as well as all the things listed before. That means gate oxide thickness, substrate doping concentration, and gate material, which also contributes to the flat band voltage. The situation complicates a little bit, and it becomes more interesting if we add those two terminals, source and drain. And what the expression from the previous slide was saying is that if we increase the voltage difference between source and bulk, then the threshold voltage is increasing. So why? The only thing we changed is added the source and drain terminals. So first thing is that we look at the threshold voltage in the second case with respect to source, and not absolutely judging the bulk to gate voltage. So that's the primary difference. But the second thing is why at all the threshold voltage is changing. So if no current flows, the depletion width has to be constant along the N+ region. So we are considering the case where we already have the inversion channel, and we will be thinking about this condition. That if we have the N+ under the gate, so we have this inversion channel, and we have then depletion region all along, then it has to be equal width. Otherwise, things get strange. And I would like to give here an example. Imagine that we have a fixed body and fixed gate voltages, and then source and drain, we start increasing. So what happens is that the drain and source diodes become more reverse bias, and the depletion region width is increasing. So that means that the band diagram, which you can see in the right-hand side top corner, the band diagram, it's bent more and more between P and N. There is a higher difference in the energy levels. So end conduction and valence band on the N side are going down with respect to P side. And this is the band diagram only close to source or close to drain. And now what happens close to the gate? In the gate, suppose the depletion region was then, it wouldn't change. So the energy level under the gate would be somewhat higher than the energy levels close to source and drain. Then all the electrons that are under the gate, they would look into the source side and they would say, hey, there is a lower energy level I can get to without much effort, and they would sweep down this energy slide, and all the electrons would try to get to the N and source region. And with that, that will lead to equalizing of the energy level all along the channel. So between drain, from drain, through under the gate to the source. And until that happens, we have to keep increasing the gate voltage to create more electrons, because until that happens, the electrons will be going away to the source and the drain side. And effectively, that's equivalent to saying that we have to increase the threshold. We have to see it as increased threshold voltage in order to achieve the same condition. So having spoken about the threshold voltage, we can go to the next topic, which is IV characteristics, the drain current as a function of drain source voltage. So we have already seen the expression of what it is in the, how the current changes in the linear region and the saturation, and we will be repeating it a little bit. Basically, in the saturation region, the characteristics are flat, but almost flat, and we go to that. And that current level only depends on the gate to source voltage, whether in the linear region, we had this parabolic expression describing the drain current, and what I would like to discuss in the next slide is that we can make some approximation about the on resistance, that actually for very low VDS currents, we can also think about it as almost linear dependency. Here I would like to stop just for good reminding on the border between the linear and saturation region. So the dotted line, dashed line, that shows the pinch of condition for different gate voltages. And this condition changes also in parabola. And the crossing of the dotted line with the IV characteristics is exactly the point where VDS, the drain to source voltage, is equal to VGS minus VTH. So in the linear region, when we go to especially very low drain to source voltages, we have this almost linear dependency. And generally the expression for the linear region, which is the quadratic one, so depending from which side we talk about it, it's quadratic one. And we have the influence, of course, of the gate to source voltage, transistor width, length, mobility, oxide capacitance, threshold voltage. And then we have drain to source voltage minus this squared VDS voltage term. And if we go to VDS, that is really, really low, so low that the VDS is much, much lower than 2 times VGS minus VTH, then the red term, VDS square, we can neglect, because then VDS square will be much, much lower than VGS minus VTH times VDS. So our equation can simplify to VGS minus VTH times VDS without this, of course, with the coefficient at the start. And if we look at this current equation in this format, then we can recall what is the expression for resistance, the linear dependency of current and voltage, and we can see that between the IDS and VDS there is actually just the linear dependency, and this linear dependency is the coefficient but inverted. So 1 over mobility times oxide capacitance times dimensions W over L times VGS minus VTH. So this on resistance will, of course, depend on what gate source voltage we have applied, and that's why the slope of the resistance will change and will increase for increasing gate to source voltages. And this approximation is something that we are using very often in analyzing digital circuits, because if we have, for example, inverter, we will look at this example later also in the application of MOSFET transistor into simple circuits. We will have a bottom transistor, for example, switched off, upper transistor switched on, and this, if there is any current drawn from this gate, it will be corresponding to this on resistance of the transistor that is fully switched on, because digital circuits, they basically, the input voltage goes between fully off, fully zero, or that means on for PMOS transistor, and VDD power supply. So therefore, it's also useful approximation, and approximations actually are always useful to know, to shorten the way for hand calculations. Then we have an interesting topic on the saturation region, and this interesting thing is that we can see, so on purpose I don't make some draft of sketch how these characteristics look like, but these are simulation results, and we could see in the previous slides it's for a NMOS transistor with 5 nanometer gate oxide thickness, and the width and length of the channel both equal 5 micrometers. So in saturation region, we see that as we increase the drain to source voltage, then the current is somewhat also increasing, even though in the theoretical part in the last part, in the basics of MOSFET transistor, what we could see is that actually it's flat and it's independent, and there was of the drain to source voltage, and I was giving the example of the waterfall. And now we see that actually it's not quite right. And to correct for this increase in the current, we are adding in our model the simple component of 1 plus lambda times VDS, and it corrects the current for the increasing dependent on the drain to source voltage. Now I would like to give again an intuitive explanation of why that happens. So as we increase the drain to source voltage, so normally we have the inversion charge under the gate. And as we increase drain to source voltage with respect to gate, so in case of PMOS transistor, actually we're decreasing. In this example, I want to let us think a bit more. Well, let's go to the opposite side, and not NMOS but PMOS transistor. So we are decreasing the voltage source, and at some point it's lower than the gate, and also the difference between gate and drain is such that there is the drain, it's to drain gate voltage, it becomes smaller than threshold voltage. So we have a disappearing charge under the gate, the disappearing inversion layer, and we have just the depletion. And as we further decrease drain, then we will have this pinch-off point moving closer and closer to the source. And if we think about the inverted part of the channel as certain resistance, then this resistance is going to get smaller and smaller with decreasing drain voltage. So the resistance is getting smaller, voltage is constant at the pinch-off point, so drain voltage is decreasing, source is constant, and the pinch-off point is constant. Just the distance between source and the pinch-off is smaller, so the resistance is decreasing. So if we think about Ohm's law, the voltage pinch-off is constant, resistance is decreasing, so the current has to increase to compensate for that change. And that will be this corresponding increase in the saturation region related to the channel length modulation. So that would be the intuitive view on that. The next topic regarding the saturation region is transconductance. That's by no means a second-order effect. That's just something useful why we love transistors as active elements, because this tells us about the ability to amplify the signal. And what we come back to is the transfer characteristics. That means the current as a function of gate to source voltage. So we see that the threshold voltage, it's at some point where below the threshold voltage the current still is flowing. Then as we increase the gate to source voltage, the current doesn't only keep increasing, it flattens out. And we were also discussing the reasons why that happens, because the saturation of mobility of the charge carriers, and because of the electric field, the scattering effect, so the mobility is not the same value anymore. And what we can do with this plot is take a plotted derivative of IDS as a function of VGS and plot this orange line, which is just increasing because the characteristics becomes more and more steep, and it reaches some maximum point, and at some point when the characteristic starts to flatten out, then it decreases again. What is maybe interesting to mention here is that we can use this maximum point in the derivative, and at that point, draw the line as it's shown, the dotted line, which meets the x-axis, and that will be the VTH, and that will be one of the ways that in practice we will have extracted the threshold voltage. So not according to the definitions that we were using before, but in practice based on the measurement. There are also other methods. We do that differently in the differently in the saturation region. But that's also interesting to know that there is some relation to that. But what I would like to point out is what this derivative is related to. So this tells us about the parameter called GM, which is the transconductance. And as you can see, then the value of the transconductance depends on the operating point. Depends where we are on the gate to source voltage bias, the transconductance has different value. And this GM parameter, that is transconductance, tells us how well device converts gate voltage signal to drain current signal. If transconductance is high, that means that small variation of the gate to source voltage will translate to very large current swing at the output, if that's output in our circuit. So with that property, we can use it as amplifier. So we will apply small signal from some sensor at the gate, usually over capacitance because, or in a differential structure, because we also have to make sure that the gate voltage is biased. So that's maybe more, slightly more advanced circuit point of view on that. And then the current that we have to read out, we can run this current over certain larger resistance and then connect analog to digital converter, but the voltage drop will be much larger on the output large resistance times the large variations current than the input signal. So that would be our idea of using the transistors, and we always want to think about this parameter to be of large value. In some cases, especially when we want to have the current, circuits of low power consumption, we are interested in operating in the subthreshold region. That's something I already said before. But the subthreshold operation region, also analyzing it and looking at the characteristics in subthreshold, we can also understand what will be the current value if the transistor is switched off. And as an example, you can see here again the same characteristics that we were looking for transconductance, the current as a function of gates to source voltage, and the same, exactly same data, but plot in the logarithmic scale for the current. And then we can see the quite characteristic feature is that in the logarithmic scale, the characteristic here is linear. So as the VGS increases, the logarithm of the current increases linearly with VGS. And at some point it starts bending. So as long as it's linear, we are in weak inversion, then we go through moderate inversion to the threshold condition, and onwards we have strong inversion. So we define this subthreshold. We speak about this linear part in the logarithmic characteristic of the semilog plot. We can characterize it by the so-called subthreshold slope. And the subthreshold slope is, tells us how much voltage we have to apply at the gate to source, at the gate with respect to source, in order to change current by 1 decade. And generally, we would like this to be as steep as possible, to have a possibly small value of S. So if we have a small value of S and steep subthreshold slope, that means that when we know just that about our process, then we will know that, okay, if the transistor is, the difference in current between fully off and fully on will be huge. And we are interested in having high current capability, the high current drive capability when the transistor is fully on. So it also will have a low on resistance. And when it's fully off, we want to have a low leakage current. Here, there is a cited example why low off-state current is important. So imagine that every transistor in a large integrated system would have just 10 nanoamp of leakage current between drain and source. And then if there is 1 million CMOS inverters, then the static power consumption will be 10 milliampere. And of course, there will be not just 1 million inverters, there will be other gates, so the calculation might be more complex. There might be much, much bigger systems than that. So generally, it might come to very large current, static current consumption if we don't take care to minimize it. On top of the static power consumption, of course, we have even more significant dynamic power consumption related to switching action of the system ongoing. So you know it probably from your own experience that when we want to have a processor in the computer going on a certain frequency, we would like to increase it, then we have to have better cooling because the power dissipation is so high that everything is heating up much more. But even the static power consumption, that's what we have also to take into account. So we would like to optimize the sub-threshold operation so that the characteristics are as steep as possible. So the first thing, what's worth knowing is that there is a fundamental limit of the subthreshold slope. And the subthreshold slope can be described with this fundamental limit as eta times 60 millivolts times the temperature divided by 300, so the room temperature operation. So one thing we can do to increase the subthreshold, the S parameter, and to have a steeper characteristic is to run at lower temperatures. And the second thing we would like to do is to have the eta parameter as low as possible. And the limit here is 1. We cannot have lower than 1. That's why at room temperature, the fundamental limit is 60 millivolts. And it can only get worse depending how we design how the transistor is designed. Another thing that can be done, which So there are two parameters to play with. One, as a person who can select from different transistors available in the process, or a process engineer who is choosing tuning the doping, or the whole team of engineers. And another thing is we can change also the body bias voltage. And everything comes to the structure of the two series capacitors. We have gate oxide capacitor, and we have depletion capacitor. And what we would like to have is that as we modify the gate voltage, we would like that the surface potential in the channel, it's also tracking the gate voltage. But because of the depletion capacitor, it won't be quite like that. We have this capacitive divider. So, which is COX divided by COX plus the depletion capacitance. So we would like the depletion capacitance to be as low as possible. Then we have a value of eta closer to 1. And so what we can do to have a low depletion capacitance is one thing, increase the body bias, so make more negative biased bulk, so lower for NMOS transistor or higher for PMOS transistor. Or there is a large playroom with the doping level. And what you can see here is a draft based on the source where we can see details of such simulation, where the doping level is changed, and we look how the drain current as a function of gate voltage, the transfer characteristic, how it's changing. So if we have moderate doping levels, but rather low, that's the best situation. We would like generally to be as low as possible, but at some point, so the depletion capacitance would be just smaller, but at some point we have a situation that the depletion region, especially for short transistors, that will be a problem, that the depletion region from the source and the one from the drain, they will be coming close to each other and nearly touching. So we are going to lose control over the gate. And that will be also the problem in gate technologies, regardless of this variable doping simulation. So it's not a noteworthy point. However, if we increase the doping capacitance, the doping level, then obviously the depletion region gets thinner, and therefore also the capacitance it's larger. So we have a degradation of these subthreshold characteristics. What I would like to add in the comment also from the previous slide, we have the expression of the drain to source current. You can find, if you look into several books, you can see that there are some discrepancies. Sometimes also there is no drain to source voltage taken into account. And there are several different formulas that you can find in this case. What is important is that in this case, the charge carriers are mainly thermally generated charge carriers. So we have a very strong dependency on the thermal voltage, which is kT over Q. We have strong dependencies of the doping levels, which you can see in the presence of eta parameter in the exponent. And the charge carriers are, transport is based on diffusion. So that's why also in the subthreshold, when we look on the characteristics, they are linear and diode, which the forward bias is also dominated by diffusion. If we take the logarithm of current of the diode, plotted as a function of gate to source voltage, also we have this linear behavior. And that's because in both cases we have the diffusion current dominating the charge transport. For the subthreshold operation, I also give here measurements done in cooperation of our institute, where you can see how in scaled technology nodes with the power supply of only 0.9 volts for different size transistors, how the current looks like. So we are not anymore at 5 nanometers gate thickness as one of the previous examples, but here it's closer to like 1 nanometer effective gate oxide thickness. And how much more details we can read from the transistor, how much we can learn about the transistor if we look also on the subthreshold characteristic and the logarithmic scale. So in the linear scale, maybe we can extract the threshold voltage, but we can learn much more when we also analyze the characteristics at low current. And since there was a discussion for the subthreshold voltage about the importance of the depletion capacitance, the next point that I find important is to look altogether at the topic of the MOS gate capacitance, also other capacitances related to MOSFET structure. And here again, comparing the MOS structure and MOS transistor structure, what will be the differences from the point of view of the gate terminal in terms of the capacitance. So in both cases, we can consider those 3 steps where first we have the accumulation, so the gate voltage in case of N channel much lower than 0, much lower than bulk in this case, or source. Then as we approach the threshold voltage, the middle case is that we start creating the depletion region. And then above the threshold voltage, we have channel under the gate. We have inversion. And what we can see is that what we can look at it as equivalent capacitances that are related to the gate oxide and the depletion region. So in the accumulation region, we only have the oxide capacitance because there is no depletion yet. When we create the depletion region by increasing the gate voltage, we have the series connection of gate oxide capacitance and depletion capacitance, looking from the point of view of the gate. And then as we further increase the gate voltage and we have the inversion under the gate, then still for the CMOS capacitor, we have this series connection of oxide capacitance and depletion capacitance. But if we are looking from the perspective of the gate and we consider the MOS field effect transistor structure with drain and source, then the channel is connected, there is electrical low ohmic connection between source, drain, and channel. And then the depletion capacitance is shielded. So from the gate point of view, we have again in the inversion, in the strong inversion, we have only gate oxide capacitance. And what is nicer is to illustrate it, to look at so-called CV characteristics, capacitance voltage. So what we can, similarly, like we had the transfer characteristics where we were looking at the current as a function of gate to source voltage, we can look at the capacitance, the gate capacitance, how it changes as a function of the gate to source voltage. And the thing is that it's not exactly the same for this MOS capacitor structure and MOSFET with drain and source doping regions. So first, in the accumulation, we have the highest possible capacitance because it's just gate oxide capacitance. And as we reach the flat band condition, where we start building up this depletion region, the depletion capacitance will be coming into the play, and also because of the series connection of the oxide capacitance and depletion capacitance, which gets lower and lower, we see that the capacitance, the overall gate capacitance, is decreasing. So the more the band diagrams bend, and at some point we reach the inversion point, which then goes into, we will observe the steep increase in the characteristics, and then in the strong inversion for the MOSFET transistor, we're going to see again just this oxide capacitor, just as we have seen in the previous slide with the equivalent capacitances drawn on the circuit. The depletion capacitance is shielded by the channel. So we are back to the small capacitance. However, if we consider the MOS structure, the capacitor without drain and source, then we still have the depletion capacitance. And the depletion capacitance means that there is the level at which everything saturates, and we are continuously at the very low capacitors level. Here, we have a little bit of influence of the characteristic of the signal. So especially if the frequency gets very low, so we are at low frequencies, such that the charge carriers in the bulk, which we are not having lots of carriers, because of, we are talking about the depletion region, and minority charge carriers, so we are really speaking about low number of electrons, for example, in case of p-type substrate, then we have to go to very low frequencies so that the gate signal can be, the charge carriers can follow the gate signal. And if we are at sufficiently low frequencies, then the depletion capacitance will become negligible. It will be as if it was not there because charge carriers can follow. And in that case, the characteristics are high. And of course, if we are in some intermediate frequencies, we will see the whole family of characteristics that is in between. And what's really great about these characteristics and those specific points of where the characteristic bend is that we can also use this characteristic for extracting such parameters in the transistor as threshold voltage and the flat band voltage. So we can learn about the process from this kind of characteristics. So that will be from the gate perspective of the gate terminal. But if we are thinking on the circuit level, then very often we want to understand what are capacitances related to different terminals. So if we take this MOS transistor structure, we can draw characteristic capacitances, so which can be also estimated in the value. And of course, all the circuit simulation transistor models also have to model these capacitances. And there will be, so C1 through C2, so on to C6. So the first one is the gate capacitance that we already seen in the previous slides. So this is dependent on the oxide thickness, also oxide material. It doesn't have to be necessarily silicon dioxide. There are also modern processes they're using, for example, hafnium dioxide. Then gate capacitance is also dependent on the size of the gate, so the physical dimensions. Then the depletion capacitance, so C3 and C4, let's start with that because it's also like related to gate, but it's this overlap capacitance over drain and gate. So it's not directly related part to the bulk, and from the source point of view, it will be the important capacitance, or from the drain point of view. So C4 and C3. Then C2 is the depletion capacitance under the gate. And then we have also depletion capacitances related to the source and related to the drain. And depending from which perspective of which terminal we're looking at this for the circuit analysis purposes, for example, we can think of those capacitances with relation to the terminal-to-terminal capacitances. So we will have the gate-to-drain capacitance, drain-to-bulk, and similarly gate-to-source, source-to-bulk, and also gate-to-bulk capacitances. So from the geometrical point of view, the C1 and C2, so gate and bulk related capacitances, they will be depending both on the width and the length of the transistor. The source and drain capacitances, they will be, in the layout we can make the source or drain doping region. It's possible to make it wider. So for low capacitances we want to make it small, but there are different compromises. But generally it's mainly dependent on the width of the transistor. And similar, the overlap capacitance, it's also depending mainly on the width of the transistor and how much the gate overlaps with drain and source. That's a technological property that it's given typically for circuit design. We have data sheet about the process which tells us how severe this overlap capacitance is. And as an example where this capacitance might be important is, let's consider we have such amplifier circuit where we care about high transconductance so that the small signal at the input will translate to high currents through the drain, and the output step, the output will be also large. So with the gate source and gate bulk capacitances, any source, so the V-in is at the bottom of the source resistance. So this source resistance together with gate capacitances will influence the slew rate at the input of the transistor, whereas the drain-related capacitances will end, of course, in combination with the on resistance of the transistor, and the load resistance will be will determine what is the slew rate on the slew rate of the output signal. And so the dominating influence of this timing characteristics is the capacitance. And you might be interested, what about the speed of the charge carriers? So I'm not giving here the typical comparison of the typical capacitances, but just one, so because for different circuits, this is going to be quite varying quite a lot. But what is what I have been looking up in some literature, scientific literature, is what is the velocity that the electrons can achieve, like maximum velocities, and it goes between up to 0.1 to 1 times 10 to the power of 7 of centimeters per second. If we recalculate that and we think about transistors that are sub 100 nanometers, where really the capacitances are getting smaller and smaller, because for large transistors the capacitance is larger. The transit time will be also longer, but incomparably, the capacitances are larger. So if we have sub-100 nanometer transistor, then the transit time will be less than picoseconds. And surely the capacitance will be dominating. So therefore, we can reach in the silicon, that's for silicon. So in the silicon, we can reach gigahertz speed for the operation. If we want higher speeds, then we need to change. We have to have some better charge carrier mobility characteristics, and we have to change to different type of material. So if you're also interested in that, there is a further reading, Muhr's law, the future of silicon microelectronics, which is, there are some topics relevant to this speed of switching, but also for the future topics that we are still going to discuss about the technology scaling, it's also relevant literature. So let's pass to the last point in this lecture, which is simple and practical application of MOSFET transistor in circuits. The simplest one, and I don't know if the simplest, probably, but also the most obvious, and this is also why we are talking so much about CMOS technologies, is because of the CMOS logic gates, with the simplest of those gates being the inverter. So we can see here the cross-section of the inverter with N-channel and P-channel transistors. The drains are connected, gates are connected, and then we have this N-well region, N-type doped for the PMOS transistor, so that we can apply, so that it actually works. We need the PMOS to be in N-well and NMOS to be in P-type substrate. If we apply high voltage at the gate, and 5 voltage at the power supply, which is connected to the bulk of the PMOS, and 0 volts at the bulk of the NMOS transistor, with the respective bulks and sources shorted, then N-channel transistor will be fully on. Hopefully that for CMOS, the threshold voltage is in the range of sub 1 volt. The N-channel is fully on. So it's pulling the output to ground, and typically in CMOS stages, the next level, it will be just capacity float. It doesn't have to provide drive current except for leakage current for the next stage. So there is not much stopping the NMOS transistor from pulling it down, except possibly PMOS. But let's see what happens with the P-channel transistor. If we have we are talking about 5 volts at the input. So 5 volts at the gate and 5 at the source. That means that the transistor is in off state. So we have accumulation. We are far from the strong threshold conditions by no means. So the transistor is off and provides no current. So the voltage at the output is 0. And if the input changes to low level, then we have the opposite situation, that the MOSFET transistor gate goes down to 0, the MOSFET is off, the PMOS transistor gate to source voltage becomes suddenly large, and the PMOS transistor pulls the output voltage high. And like that, we have this feature of inverting the logic level from high at the input to low output, or low input to high output. For making immediately, having understood one circuit and making application for what more we can do on the circuit level, except from going to logic gates, we can do AND, NAND, and then add soon flip-flops. Actually, here is something similar to a flip-flop. So a SRAM memory cell, so a cell which is holding the logical state. So if we have 2 inverters, and the first one has input high, then it has low output, and the next one has low output, it will have low input, high output, and the second stage is high input, it will have low output, and if we close them in the loop, then it's a self-sustaining structure. As long as the power supply is on, then we keep the memory value. So that would be the SRAM, so-called SRAM memory cell. Another thing we can do with inverters is connect them in the even number, and then we have a unstable structure because we have from low to high, low, and then low wants to change to high, which means that the input will change again. So it keeps oscillating the structure, and this is something that is very broadly used for clock conditioning of clock signals in phase lock loops in modern circuits. This structure will be explored, and there can be lots of peripheries added so that the frequency of the oscillation stays stable. Generally, what we always look at for the ring oscillator is what is the on resistance and what is the load capacitance. So if we want to achieve the high speed of the frequency, we need to have small number of stages, so the minimum is 3 that we can do. We want to use the smallest size transistors to have the low capacitance. On the other hand, we want to have low on resistance, so for that the transistor, I don't know, maybe we are going to use the minimum, or maybe extend the width of the transistor and use the minimum channel length so as to reduce the on resistance. And with the on resistance and the capacitance, we can determine the rise and fall time on each individual block. In fact, in practice, such structures are used with, for example, current starving or charge pump regulating the power supply, because we really want the frequency to be stable with the operating conditions. So operating conditions. The power supply level might change. There might be some noise on the power supply, and we want it to be independent on the noise. And also there are temperature variations, and we have seen that the threshold voltage, for example, it's highly dependent on the temperature. So because of that, the characteristics also will be changing with the temperature. Also, the charge transport properties also are depending on the temperature. So there are things to do behind, but that's the basic concept, the ring oscillator. So before the ring oscillator, we had the first type of the memory cell, which is the SRAM, the 6 transistor structure. Another type of the memory is the DRAM, where we have a capacitor and the access gate. So either we switch on the transistor to write in the value into the capacitor, or we close it and we keep the value stored in the capacitor. And it's actually very similar concept and similar considerations what we are using in the sample and hold stage, where we sample a signal and then have it stored on the capacitor, not just to read out the capacitor value at any point later as it's done in DRAM, but as soon as analog to digital converter that it's following the capacitor is available, and it takes finite time to read the value of the capacitor, it converts the stored charge on the capacitor, storage voltage, to digital value, so that we can then consider it for data processing. And then what we can see here, there are those two phases oscillating for gate voltage. The pattern and the duration is very much dependent on what we are talking about. For DRAM, we need to have regular refresh to reprogram the voltage. In this case, the example is for sample and hold, where we have not just digital value like for DRAM 0 or high that is being stored, but we have something more complicated. There is an input voltage that we want to sample, and during the hold time, maybe there is another gate on the other side of the capacitor that goes to the digital to analog converter to read the voltage. And there are those two sets of parameters during the Sample time, we would like that this sampling takes as short time as possible. So we care about low time constant. That means the capacitance, maybe we can adapt and have a larger value of capacitance gives us better hold time properties. But in this case, for sampling, we would like it to be small CS and small R-on. That gives low sampling time. So that also very much depends on what parameters for the transmission gate we have chosen. We would like large W over L. But then there is a compromise what happens in the hold time. When we have large width of the transistor, then it's much more potential for, so it's more powerful in terms of leakage current. Because if small transistor has leakage current, 10 times bigger transistor will have 10 times higher leakage current. And the leakage current, what you can see at these characteristics, the purple line, which is the sampled signal, it's discharging during the holding time. And that's because of the leakage current in our transmission gate. So for one thing, is the leakage current between the drain and source. So that's what follows the subthreshold operation expression, depending on all the same as here. And we have a bulk leakage current related to drain bulk diode. And in this case, it's all what we have learned about reverse bias diode and the dark currents in the diode. In principle, if you want to have a good sample that holds circuit, having good properties during the hold time, it would be great to quickly cool it down for the hold time. No, it doesn't work. But low temperature helps with the leakage current. And at the end, just because I think it's interesting to know about those two types of memory cells, we had the locked inverter structure, and also we had the transistor capacitor structure, so-called SRAM and DRAM cell. So SRAM will be 6 transistors, because we have 2 transistors in each inverter, that means 4, and also we have 2 transistors to access those 2 nodes. So during the programming or reading of the structure, we need to have access. So that makes 4 transistors in total. Whereas the single 1T, it's obvious the transistor is drawn. In the first place, for SRAM, the stored value is actively maintained. As long as the power supply is there, the value in the memory is stored. However, the area of the cells, because of the 6 transistors, it's quite large. And typically, we have those 2 nodes, and the readout is done in the differential manner. The second cell, it theoretically, as long as the transistor is switched off, it doesn't need any additional power, but however, still it works in the operation because it needs periodical refresh. But really the great benefit is that we can make those cells very small, and in fact the processes which are adjusted for this kind of DRAM cell, they have special capacitance, options which are not available in the standard CMOS, but will have a very compact capacitance. Very often they are 3D structures, so not just done with the planar technologies. And then the single transistor and the capacitor can be integrated in the very dense, small area, and then we can have much denser memory cell per unit area. And I will speak maybe a little bit more, not specifically about this type of memory, but about also technologies related to its fabrication, because in the advanced technologies where we care also about the density of the memories that we are all using daily, exchanging data and working with our computers, to have a dense memory per unit area, one thing that can be done is also 3D integration, so stacking multiple dies, so not only making it smaller in terms of area, but also making it 3D. And that will be also topic in the next parts of the remaining course. And with that, I would like to thank you for attention, listening to this part.
You're the signal in my static hum, a perfect match we've overcome. Wires crossed, but we still